Hello friends, in this session we are going to learn about a device which is called as galvanometer. Now galvanometer is a device which is used to detect the current. Now why have I used the word detect? Because this galvanometer is used to measure a very small amount of current, maybe in microamperes. Now what exactly is there inside the galvanometer? We are going to understand the basic construction of the galvanometer and the working of galvanometer. Now inside the galvanometer, take any type of galvanometer. Inside this galvanometer, we have two magnets. Okay. This is North Pole and this is South Pole. And we have a rectangular frame, rectangular coil, which can have n number of turns, right? We can have n number of turns in this particular coil, rectangular coil. Okay, let me name the rectangular coil A, B, C and D, right? Okay, now this is the pictorial the representation of galvanometer, but exactly in the actual galvanometer, these two magnets actually produces radial magnetic field, right? But just to make you explain the basics of galvanometer, we have considered such kind of a magnetic field. Inside the actual galvanometer, we have radial magnetic field, so that this magnetic field lines always pass perpendicular to the conducting wire, right? Okay. So the magnetic field outside the magnet, it moves from what? North pole to South pole. So this is the magnetic field, right? This is the magnetic field B, right? Now what will happen if a current carrying conductor is placed inside the magnetic field? Now what I am doing is, I am connecting a wire to this rectangular coil, and due to this wire the current is flowing in this rectangular coil. Let's say for example the current I is flowing in this particular direction, right? What will happen if a current carrying conductor is placed inside the magnetic field? You know, force will be acting on it. What is this force given by? This force is given by F is equal to Bill sin theta, right? B stands for magnetic field, I stands for current, L is the length of the conductor, and theta is nothing but what? The angle, right? Okay, now in this particular case, what is the angle between L and B, right? This is L and this is B. It is nothing but what? 90 degrees. In case of A and B, for this particular length A and B, what is the angle? It is 90 degree, right? So I can write force acting on A and B, force acting on A and B, FAB is equal to sin 90 is what? 1. It is equal to Bill, right? Force acting on A and D, what is the angle? The angle is 0. If the angle is 0, the force will be equal to 0. So that means there is no force acting on A and D. So force acting on A and D is equal to what? 0. In the same way, what is the force which is acting between acting on the conductor D and C? The force acting on the conductor D and C is again, what is the angle? 90 degree. So sin 90 is 0. It is equal to BIL, right? What is the force acting on BC? Again 0. Why? Because in this particular case the angle is said to be what? 180. Sin 180 is equal to 0. So that means this FBC is also equal to 0. That means we have two forces, that is FAB and FDC. Now what is the direction of this force FAB? The direction of this force can be given by the help of Fleming's left hand rule, right? So how is Fleming's left hand rule given by, right? Take your left hand and the three fingers should be perpendicular to each other. Thumb indicates force, pointer indicates magnetic field, and middle finger indicates current. How to remember this? FBI, right? Force, magnetic field and current. Or you can also remember this by an abbreviation F, father, mother, child. Father, F, stands for force. Mother, M, stands for magnetic field. Child, C, stands for current. Right? Okay. Now I am using the same Fleming's left hand rule on part AB of this coil and understand what is the direction of the current, right? So I want to find the direction of the force. I know what is the direction of magnetic field. I know what is the direction of the current. Magnetic field is in this direction, current is in this direction. That means, what is the direction of the force? The direction of the force is inside. That means this particular part of the coil is going inside, right? Inside the plane. Okay, what about this particular part? This is the direction of the magnetic field and this is the direction of the current. What does the thumb represents? Force. That means this particular part, D and C, is coming out of the plane of this glass, right? So that means this part is going inside and this part is coming outside. That means basically this coil will rotate, right? Why? Because torque is acting on this particular point. On this coil, and since this coil is rotating, what I am doing is I am attaching a needle to this rectangular coil. The moment the coil will rotate, the needle of the galvanometer will also rotate, right? Now since this torque depends on current, the needle will show corresponding deflection in accordance to the current. If the current is more, the needle, the rotation will be more. Why? Because the torque will be more, the rotation will be more. If the rotation is more, the needle will show more deflection. If current is less, then torque is less. If torque is less, then less rotation. If less rotation, less deflection of the needle. Right? We will understand this thoroughly. Okay. Now, how is torque been given? This length is L. Okay. AB is L and DC is also L. And this is B, right? Okay, okay, and this is what? L. This length is L. We have indicated it as what? Capital L. So this is what? Capital L. Okay. Now, what is torque given by? Torque is equal to R vector. Torque vector is equal to R vector cross F vector. So, what is the magnitude of the torque given? The magnitude of the torque is given by RF sine theta. Okay. Now, what is theta? Theta is nothing but what? Angle between R and F. In this particular case, what is R? This is the distance between the two forces, perpendicular distance between two forces, right? This is a force FDC and this is the force FBA. So, I can take tau as perpendicular distance, which is nothing but what? B. And what is the force? I can take any of the force. So I'll take F, B, A, B, right? Because both the forces are what? Having equal magnitude into sine. What is the angle between B and F? This force is having an angle of 90 degrees. So it is what? Sine 90. Sine 90 is 1. So that is what is tau? Tau is nothing but what? FAB, or I can say FDC into B, right? So, what is tau? Tau in this particular case is equal to F is nothing but what? BIL into small b, right? Okay. Now, what is the L into B? L into B is nothing but what? L into B is nothing but what? The area of this coil. So I can write tau is equal to BIA, right? Now, if I am having n number of turns, then what will be tau? Tau will be given by Bina, right? So tau is equal to Bina. So this is nothing but the torque with which this rectangular coil will rotate. Now, right? Okay. Now, if I is equal to 0, this torque completely depends on what? Current, right? Not completely. I can say it also depends on current. If current increases, then the torque will increase. If the current decreases, torque will decrease, right? Now, this particular rectangular coil is also supported by a spring, right? A helical spring. Because if let's say for example I am passing current through this rectangular coil, right? This coil will rotate. However, if I stop the current immediately, if I disconnect the circuit and stop the current, the coil will still rotate because of inertia. So what will happen? The needle will still show the deflection because of inertia. Although the current has become zero, the coil will, the needle will show deflection. So to stop the coil from rotating, we will have a helical spring which will provide a restoring torque, right? So this helical spring will provide a restoring torque in opposite direction. So I can write tau r, this is nothing but the restoring torque, is equal to C into theta, right? C is nothing but what called as torsional constant and theta is nothing but what? The angle of deflection, right? More this coil will rotate, more this needle will get deflected. More the needle will get deflected, more restoring torque will be there in the helical spring, right? Okay, so that means this restoring torque is directly proportional to what? Theta, deflection. But C is nothing but what? Torsional constant, because this torque also depends on the material of this spring, material of this helical spring, right? So restoring torque is equal to what? C into theta. Now this restoring torque have to balance this torque, right? Because this torque and this two torque are opposite in direction, because of which this coil will stop rotating the moment it becomes equal to restoring torque, right? So I can say, so this torque is equal to restoring torque. So I can say Bina is equal to C into theta. So I can say I is equal to C upon BNA into theta. Now C is torsional constant, right? Which is constant. It depends on the material of helical spring. B is magnetic field inside the galvanometer. It is constant. N is the number of turns of the rectangular coil. It is constant. It is not going to change. A is what? The area of the coil. It is not going to change. So I can say I is directly proportional to theta, right? So that means if I am providing more amount of current, more will be the deflection of the needle. Less amount of the current, less will be the deflection in the needle. This is actually what is desired in the galvanometer, right? So this is how basically a galvanometer works, right? But there are few constraints of the galvanometer. We cannot pass a huge amount of current inside the galvanometer because the coil of the galvanometer is very sensitive. If we attempt to pass a huge amount of current in the galvanometer, the coil of the galvanometer may get damaged and the galvanometer itself may get damaged, right? So that's the reason why we are supposed to, in order to measure more amount of current, we are supposed to convert galvanometer into ammeter, right? I hope you have understood the session. Thanks a lot.